So, like Kurt, I grew up learning math from Milnor's books. I studied them as graduate students. I've taught courses out of them. In some ways, it was those books that taught me how to break down a mathematical problem into simple terms and how to think about mathematics. When I was in graduate school, I used to struggle to wonder what it is that makes beautiful mathematics beautiful. What makes good mathematics good? How can I tell to distinguish great mathematics from mediocre mathematics? I used to wonder how come if I invent a notion of a set where there's red elements and blue elements and I can add the red ones to the blue ones, but I make up some rules that no one would care about that. And it was in Milnor's work that I think it was really my first encounter with great mathematics. And at that time, I understood something simple that stayed with me my whole life, that great mathematics produces more mathematics, and great mathematics creates connections between different fields. Great mathematics is something that grows. So from those days, Milnor has been one of my mathematical heroes, and it was a pretty overwhelming feeling to be asked to give this talk. Jack, you may have gotten the Abel Prize, but this is a pretty amazing thing to do too, to get to stand here and testify for one of your heroes. I hope everyone in this room gets a chance to do something like that one day. So I want to thank the committee for thinking of me. I want to focus today on, like in Kurt's talk, the Mandelbrot. If you zoom in on the Mandelbrot set, you'll get another copy of the Mandelbrot set. If you zoom in on Milnor's talk, you're going to get a copy of my talk. And I want to focus on one little formula in that talk that I find to be one of the most beautiful formulas in mathematics. That's a beautiful formula in physics that relates two dynamic quantities that were in different areas to a fundamental constant of nature. The formula I'm talking about was one that was produced by Kervaire and Milnor in 1963, and I've just written it as theta equals pi times b, and I'll explain what all these terms are and how they're linked through the course of this talk. But this really stands as a striking formula, and the journey in coming to grips with this it's an emblematic journey of how to think about mathematics. So let's see. I'm going to start with the term theta. So that first appears in something we've heard about in all the talks today, in Milnor's discovery of the exotic seven sphere. So this is a copy of the first line of that paper, and this is something Milnor's work is known for, its directness and its simplicity. In the title and the first line, we learn about something revolutionary in mathematics. There's no messing around. He just gets straight to the point. So Jack himself talked about the discovery of this mathematically. Kurt talked about different constructions, and I didn't know what I could add, so I decided I would attempt a reenactment. So I don't know if this is really how things happened, but here's what I picture. So this is supposed to be a seven sphere, and you can do things with it. You can twist it around, you can smush it, but you can't, if you do smooth things to it, you can't ultimately change the fact that it's round and it looks like a sphere. But if you allowed yourself to make more violent changes to it, if you allowed yourself to wrinkle it up and twist it and pull on it and wrinkle it and step on it, and this is what I imagine happened in 1956. You're stepping on it and twisting it, and you're making it really gross and dirty, and so you go to blow it up and smooth it out again. And you can see, by the time you straighten it out and smooth it back out again, you get a surface that has a completely different shape. So this can't happen. Oh, did that fall down? It's too violent. That's what happens when you make topological transformations. So you get something with a completely different shape. So this can't happen topologically. The sphere and this torus are two different shapes topologically, but I think it shows sort of the drama with which the mathematical world received this news. Dennis Sullivan told me when he was a graduate student, there was a legend going around that M.L. Artin, on hearing about this, went around saying he'd heard the worst theorem in mathematics, that the shape of the seven sphere doesn't characterize the smoothness of the seven sphere. All right, so that was supposed to illustrate some of the drama with which the math world received it. I also want to try to, in my own way, tell you about how, what it means to be homeomorphic but not diffeomorphic. And the simplest example I could find was this. Imagine that you have a piece of ribbon. It's a special kind of ribbon. It can pass through itself, but you're not allowed to tear it. So if you took a piece of ribbon like that and you pulled it off of itself and tried to make it flat, the best you could do is create something that has some twists in it. But no matter how hard you tried, you'd never be able to completely open it up to be round like that with no twists. So another way of saying it, these are related by a smooth transformation, the ribbon that's in a figure 8 and the one that's got the two twists. But the open ribbon, the untwisted one, and the figure 8 are not related by a smooth transformation. However, if you took this piece of ribbon and you started at the left end and just pulled, you'd wind up with that maneuver. You'd wind up with the ribbon transforming into the other one. So that's a continuous transformation that relates this figure 8 ribbon to a untwisted one, but it passes through something that has to have a corner. It passes through something where it doesn't make sense to take the derivative. So this, I think, this to me is the simplest illustration that kind of really captures it. It shows two things that are related by topological transformations, things that are allowed to have corners, but they cannot be transformed into each other through differentiable transformations. Now, the thing that makes this so cheap is that the whole setup here depends on structure that doesn't just live on the surface. It depends on how the ribbon is sitting in space. In Milnor's example of the seven sphere, it was intrinsic to the sphere itself. It was intrinsic to the shape you were living on and didn't depend on extraneous structure. Okay, so here's one thing a great mathematician does. Jack discovered that there was this exotic seven sphere, and the next thing you know, he decided, well, maybe I can figure out all of them. So in 1959, he produced this manuscript where he laid out the problem and a method for determining all of the smooth structures on spheres, all the possible exotic spheres. It's kind of amazingly daring, I mean, to go from just accidentally discovering one to endeavoring to find all of them. And the approach that Milnor and Kervaire and Milnor took to this problem, it changed the nature of algebraic and differential topology forever. It set it on its modern trajectory, and we're still exploring the relationships that were discovered. So I'm hoping that this talk is really understandable to everybody, but it's inevitable that I'll introduce some technical terms. I don't think you'll need to know them. I'm just putting them in to be honest, and I hope that the pictures themselves will tell enough of the story that you'll be able to really see the relationships I'm talking about. So by 1963, Kervaire and Milnor publish this amazing paper linking, in which this formula appears. And in particular, as we heard in Jack's talk, he set out and defined the problem. In fact, the definition is on the first page of this paper, but I wanted to summarize it in a little shorter. So he defined the group, which they called theta n. It's the group of exotic spheres, technically the group of homotopy n spheres up to H cobordism. I'll explain a little bit about what those words mean, but this is the set of all exotic structures on the sphere. And as it appeared in Jack's talk and in Kurt's talk, one of the remarkable things about this was the group structure. And so I have my own illustration of the connected sum. I have two of these two spheres. They might be different ones. And I can combine them into a single sphere by taking a piece of pipe and connecting them to each other using that pipe. And that is, again, that's something that's topologically a sphere. So the other thing about it is there were some very deep theorems in the late 50s and early 60s that said that H cobordism is the same as diffeomorphism and a homotopy sphere is a topological sphere. And so in the end, we know that this group theta n is exactly what I said it was. It's the study of all exotic spheres. Working out the structure of theta n is to work out all examples of exotic spheres. So in this formula, theta equals pi b, theta is the number of exotic spheres in dimensions 1 less than a multiple of 4. And the reason for restricting to that dimension will appear a little bit later. But that's what the term theta is. All right, so this has got to seem baffling to anybody. How do you possibly approach this? How do you approach determining all of these exotic spheres? And to me, this is one of the great lessons in mathematics, in how to approach mathematics. You just establish any relationship that you can. So let's imagine we're starting with a homotopy sphere, and we want to know, can we transform it into an ordinary sphere? So now I at least have two things I could attempt to relate. And then the beautiful idea that Kervaire and Milnor had was to write the homotopy sphere as the boundary of some manifold. Now, why is that a good thing to do? Why does that help us? Well, a manifold, that's a space that locally looks like Euclidean space. In a neighborhood of every point looks like a neighborhood of every other point, and it looks like we're standing in a vector space. And in particular, our ordinary sphere is living over in some other point. It's living in some other neighborhood at some other place. So at least I have, if I can get my exotic sphere to be a boundary of a manifold, at least I have a chance. At least I have a relationship between homotopy spheres and exotic spheres. I mean, exotic spheres in the ordinary sphere. Now that may not look like much, but you have to think of a great mathematician as like a ninja. As long as he can just touch his opponent with his little toe and get any relationship at all, he can defeat the opponent. And so that's, once you have any relationship at all, you have some place to go. So let's go back. We have our homotopy sphere, which I've represented by that diamond-shaped, and we've hoped that we can write it as the boundary of some sort of manifold. And now the next thing to do is to manipulate this manifold. So that what I've drawn looks like a vase laying on its side, and that differs from something like a bowl because it has a handle. And what you want to do, the idea was to somehow get rid of the handles, and a technique was introduced. Milnor introduced a technique for doing that called surgery, or now called surgery. So if you can get rid of all the handles, then your bounding manifold, it's in the shape of a bowl or something. And this isn't really a step, but I find it psychologically nice to have this picture in mind, that once I've gotten rid of the handles, I can kind of straighten out the bounding manifold. And then remember, we had our ordinary sphere someplace at the other end, and so cut a little disk out, and now you have a different relationship between our homotopy sphere and the ordinary sphere. And this is something that's known as an H-cobordism. This is the term H-cobordism that appears in the theorem, in the definition of the group. And once you have an H-cobordism by a deep theorem of Smale, you actually have a diffeomorphism between the objects occurring at the two ends. So this is the approach. And the lesson, I think, really is to imagine first any relationship at all, and then try and modify that until you get an equivalence. All right, so these are the three steps, and the other terms in the formula, theta equals pi b, will occur as we start to analyze how one approaches these steps. So the first one I want to focus on is this second step, which is getting rid of the handles. And this was a maneuver I called, as I said, it was called surgery, and it was a technique for modifying a manifold, for modifying manifolds to produce different ones. And it originates in the 1930s in the work of Pontryagin in dimension 2. Pontryagin made a famous mistake using this technique, and to my knowledge, somehow never really returned to it. And when it reappeared in Milnor's hands in connection with classifying manifolds, it became an extremely powerful tool. Well, so here's the idea. You take some manifold, I've drawn a torus, and you find in it an embedded sphere. In this case, it's just a circle. And you cut the surface open along that sphere, and you glue in two disks. Now, if I glued those green things onto the blue, I'll get something that is different. I started with something that has this shape, and at the end, I get something that's round, like the original balloon. I drew these little red arrows on there. They'll make an appearance a little bit later, so just ignore those for now. So that's one of the ways of carrying out step 2. Milnor developed this theory of surgery, and it was the main technique for changing the topology of one manifold into another, and it became eventually the cornerstone for the classification of manifolds in high dimensions. And so that term, theta, in the formula, represents the exotic spheres, but it also represents, to me, all of the amazing contributions Milnor made to differential topology. And it's truly amazing. He gave us sort of lecture notes we can follow to teach courses at, and cutting-edge research papers that are still inspiring people working in this area. I'll just mention at the Stony Brook website, there's a fantastic series of a video of Milnor's 1964 Hedrick lectures on differential topology. So you can actually go and learn the subject from Milnor himself on the web. All right, so that's the theta term. I want to now turn to the pi term in this formula. So the pi term has to do also with step 2, the step of getting rid of the handles. I'm sorry, it doesn't have to do with step 2. It has to do with step 1. The first thing we wondered, can we realize this manifold as a boundary at all? So this question exactly in this form appeared in Jack's talk as well. And Jack attributed it to René Thom, the question of when can a manifold be written as a boundary? So the remarkable thing that we learned from the work of Pontryagin, Thom, and Milnor is that this sounds like a geometric problem, but it's actually a problem in homotopy theory. And the origin of this goes back to, again, to the 1930s and the work of Pontryagin. So before the 1930s, a great deal of algebraic topology had to do with understanding the degree of a map. Or you can think of it as counting the number of solutions to a system of n equations in n unknowns. So here I've drawn a graph of a function from R1 to R1. We can think of it as a the graph of a function from Rn to itself, or even the n sphere to itself. And that green dot on the y-axis is a value, and the place where it intersects the curve are all the solutions to y equals f of x. And actually, if you look at the picture, counting the number of solutions was a fairly sophisticated idea. If I took the x-axis instead, I would say, oh, there's only one solution to the equation. If I take that green value, it looks like there's 3. And as we learn in topology or in complex variables, it's important to to count the solutions with multiplicity. Or in this picture, it's important to pay attention to those arrows. You take a value in the target y, and you arbitrarily assign a direction to it, and then you count the solution to your equation as positive if the curve crosses in the positive direction, and negative if it crosses negative, and you add up these points with signs. So in this case, I had to have +1, -1, +1, and say there's only one solution counted topologically. So in the middle of the 1930s, Pontryagin, inspired by work of Hopf and others, raised the issue of counting the number of solutions to a system of n equations in n plus k unknowns. And so I've drawn this surface as a representative of the graph of a map from a larger sphere to a smaller sphere. Now, if we do the same thing, the number of solutions will typically be infinite. But if I pick a regular value, if I pick the nicest kind of value, then that space, the space of solutions, will have the most favorable kind of geometry. It will be a manifold. And a little technical point that I need just to make an accurate statement of the result is that manifold has a little bit of extra structure represented by those red arrows. And what we say is that it's a stably framed manifold. Those red arrows represent a basis for the directions perpendicular to M inside the surface that I've drawn there. All right. So like in the case of the degree, it's important that whatever measure I'm going to make of this count has to be, I want to be independent of the choice of value y I'm taking. And if I take a different value of y, I'll get a surface, I'll get a manifold that might have a very different shape. In this case, I have 2 circles at the top and 1 circle at the bottom. But if you study the region in between, you find that these aren't random manifolds. They occur as separate boundary pieces of a single manifold. This relation is now called a cobordism, and because of the red arrows, this is technically a framed cobordism. So this notion of cobordism in this context was introduced in the 30s by Thom and picked up in the 50s and taken much, much further by Thom and others. But Pontryagin, he set up this correspondence. So I've put the explicit definition up, but just look at what's in the red circle. On the right-hand side, that's something geometric. That represents manifolds modulo the equivalence relation of cobordism. And on the right-hand side, it's an object in homotopy theory. It's the set of homotopy classes of maps between spheres, or maps up to continuous deformation. So these are really 2 objects that belong in very different areas of mathematics. And the geometric side, and our problem, when is a manifold written as a boundary, that's asking when something on the right-hand side is 0, and that translates into a question on the left-hand side. So this term pi represents an object from homotopy theory, and it enters via this correspondence of Pontryagin and Thom. And it's the order of the homotopy groups of spheres. In fact, so Kervaire and Milnor's paper relates theta, which is the group of homotopy spheres, to pi, which is the homotopy groups of spheres. And I made that joke at the beginning about E equals mc squared, where E and m are sort of dynamic quantities related by a fundamental constant of nature, I want to think of these as dynamic quantities as well, and that the theorem is saying that the number of exotic spheres is proportional to the number of maps between spheres. And so that's really a rather remarkable thing, and it relates to very different areas of mathematics. I like to think of this sort of coming to grips with this issue as sort of where algebraic topology kind of really became modern, and we started to understand the real relationships between algebraic topology and geometry and other parts of mathematics. In Pontryagin's day, there was very little known about homotopy groups, and he used the methods of differential topology in the classification of manifolds in low dimensions to say something about homotopy groups. But by the time Milnor and others started investigating exotic spheres, the relationship was reversed, and it became a much more powerful tool. So building on the work of Serre and others, and computations and information about the stable homotopy groups of spheres were able to tell us a great deal about differential topology. I think about this relationship a lot, and one of the things I want to tell you about it is that homotopy theory advanced a great deal. Our ability to understand homotopy groups sort of outpaced our ability at first to understand manifolds. But it did so by the introduction of what I like to call designer homotopy types. So take a biological example. We have biological creatures like people whose behavior we understand, but in combating diseases, you can imagine a day where we're able to specifically engineer little biological entities that'll go in with single purposes and attack diseases. So these little designer biology types they wouldn't occur in nature. Very few people would know about them, but they would be very powerful for certain purposes. And in a way, this was how algebraic topology progressed, the homotopy theory. Designer objects, mathematical objects, were introduced with very focused and very powerful purposes, but they were sort of only known by a small number of experts. And there are very few objects that are particularly convenient for understanding both sides of this fundamental correspondence. And we owe to Milnor the ability to investigate sort of the ones we do know how to investigate. So the cobordism spaces that we study in homotopy theory are the one example that kind of really lives on both sides, and Milnor gave us the techniques for analyzing them. So I've put up some text here because I wanted to make another couple points that in this era, it was an era where many of the structures in differential topology, many things that went into understanding the theory of manifolds, were being seen as problems in homotopy theory. And just the very basic tools you need to set up, just the tools of setting up the basic classifying spaces you would be interested in, the moduli spaces, the spaces that you would study if you wanted to study all manifolds of a given kind. These were the foundations for setting up all of that occur in the work of Milnor. We topologists learn about the moduli spaces that we would be interested in topology from papers of Milnor from this era. He also gave us work on the Steenrod algebra and showed us the basic tools that we use to make calculations in homotopy theory. And these are still the tools that we use today. These are still the most important, most powerful tools that we have. All right, so that's the theta and the pi. And now I want to get to this term b, which is like the fundamental constant in all of this. So this b, it also comes from trying to carry out this three-step program I talked about. So remember, the program was to exhibit our homotopy sphere as a boundary, get rid of all the handles, and then conclude that it was an ordinary sphere. And we saw that writing it as a boundary gave us the relationship with that term pi, that object of homotopy theory. And, but there's a little bit more in the problem of getting rid of the handles. So a question I skipped was, how can you possibly get rid of can you get rid of all the handles? Can you always do surgery every time you meet a handle in a manifold? And the answer is no. And here's a picture of so this is a surface passing through itself. I imagine I made a torus by taking a sheet of paper, gluing two ends together, and then gluing the opposite edges together. But every time before I glued them together, I made a figure 8. So the sheet of paper passes through itself and makes a figure 8 in one direction, and then I make a figure 8 gluing them together in the other direction. Now, in this surface, no matter how you cut it, if you cut it transverse to the edge that's facing you, or if you cut it down through the top, or even if you try to do something more ingenious by choosing a curve that wraps around the surface, no matter how you cut it, you're always going to meet a figure 8. And you can't bound a figure 8 by a disk. If you draw a cone on a figure 8, the place where the two lines cross will form a singularity, and you won't be able to attach a disk. So this is an example that tells us you can't always perform surgery. And so this is related to a phenomena, something fundamental to the theory of manifolds called Poincare duality. So I told you that locally, a manifold always looks like Euclidean space. And that means that every time I'm looking at something in dimension k, there's always something in the complementary dimension happening. If I wiggle the manifold in dimension k, I'll get a wiggle in dimension n minus k. Or a change in dimension k results in a change in dimension n minus k. So if n minus k happens to equal k, then I'm in a situation that's interacting with itself. If I make a change in the middle dimension, another change in the middle dimension will be produced. So the middle dimension, in other words, interacts with itself. And here's a picture of surgery again on a torus. So the black circle is the one I intend to do surgery on, and the yellow one is another circle, another that's in the middle dimension that's not equivalent to the one I started with. And if I do surgery on the black circle, you can see that the yellow one also changes. All right, well so this is modeled by a very beautiful algebraic structure, the intersection form, and this has also appeared in both of the other talks. So I won't bother to give you a definition, but I'll just tell you what kind of an object it is. For me, this intersection form is just going to be a vector space over the real numbers with an inner product. That is, after all, how in physics we would model a self-interacting particle. We would introduce a term that looks like something squared. And in fact, you can manufacture, as described in the other talks, a vector space out of shapes sitting on a manifold, out of cycles in the middle dimension, and it acquires an inner product because of this self-interaction. But really, for these purposes, let's just think of it as a symmetric matrix with non-zero determinant, and that matrix is recording the amount of self-interaction. Or, as I've written there, you can think of an inner product space as a vector space that interacts with itself. So there's an important invariant, an important average measure of the amount of self-intersection, and it's the number of positive values minus the number of negative eigenvalues. You can think of it as the average number of dimensions of self-interaction. And an important fact about the signature of a manifold is that it's unchanged if I perform surgery. So if we go back to our original question, is it possible to get rid of all of the handles? We can see there's a little bit of an obstruction. So let's imagine our vase M sitting on its side, and I'm trying to get rid of a handle and produce M primed, which doesn't have any handles. Well, m prime doesn't have any handles, and so the intersection form is actually identically 0. But that implies that the signature is 0. And then that, in turn, implies that the signature of my original manifold has to be 0. So there's a necessary condition for being able to get rid of all the handles, and that is that this algebraic object that's modeling the self-intersection has a 0 signature. And that turns out to be necessary and sufficient, at least if I'm in a dimension that's twice an even number. As long as the middle dimension is even, this is necessary and sufficient. So this is the thing that makes the link with number theory. There's a very beautiful formula of Hirzebruch that Jack described in his talk, expressing the signature of a manifold in terms of topological invariance. And that formula involves a Bernoulli number. And the term B in this is a scalar multiple of a Bernoulli number. Well, I guess every number is a scalar multiple of every other number, but it's that particular scalar multiple of a Bernoulli number. So there's some powers of 2, a power of 2 minus 1, and a Bernoulli number. So this then is the last term in the formula, and I just think of it as a constant of proportionality relating the group of homotopy spheres and the homotopy groups of spheres. So I'll come back in a minute and put the whole formula together, but I want to just talk a little bit more about the gateway that investigating this term B creates. And a principle emerged, and we also owe this largely to this work of Milnor. A principle emerged that structures, that the theory of manifolds is regulated by rich and intricate algebraic structures. I talked about a vector space interacting with itself, but there are much more elaborate algebraic structures that govern the theory of manifolds. Here's an example of one, and this paper is reproduced, I saw on the poster outside. This is Milnor's announcement of a counterexample to the Hauptwertmunung. And I put this here because just to indicate, in this paper, Milnor used a much deeper algebraic structure, a much more elaborate algebraic structure to distinguish two complexes from being combinatorially distinct. So I've put up some text here which you can read that testifies a little bit to some of Milnor's deep work in algebra. I want to just tell you, while you're looking at it, an anecdote. I ran into Hyman Bass a couple of weeks ago, and who wrote a paper with Milnor and Sayre on the congruent subgroup problem. And I asked him what it was like working with Jack and how it was that he became such a great algebraist. And Hyman said, Milnor just liked to think about any problem, but he always went back to the basics, and that he approached everything by reducing it to the simplest, most basic questions, and by the time he was done asking the basic questions, you felt like you'd never thought about the area before. And Milnor wrote many deep papers in algebra. The congruent subgroup problem is a famous one. It asks about subgroups of finite index in groups of matrices, like groups of n by n matrices over the integers or other things like that. I mean, it's a phenomenal piece of mathematics. I've put up here another famous paper of Milnor's on algebraic K-theory and quadratic forms. I mean, Milnor also introduced and wrote a whole book making algebraic K-theory, getting that field off the ground. But I put this up to just point out again his succinctness and how much he manages to get on the first page of a paper. So there's a dotted line there that indicates I cut out one sentence. I could have put it all on, this is all on the first page of the paper. So right here in the second sentence, he defines what we now call Milnor K-theory. Milnor K-theory is absolutely fundamental to how the methods of homotopy theory are used in algebraic geometry, and it was eventually seen by Suslin as being part of just what you mean by the analog of homology in algebraic geometry. A little bit further down the page, he makes a conjecture relating the ring of quadratic modules to this Milnor K-theory, or what we now call Milnor K-theory. I guess, Jack, you didn't call it that. And a little further down, he makes what became known as the Milnor conjecture relating Milnor K-theory to the cohomology of a Galois group. And this is the conjecture that Voevodsky proved. The other Milnor conjecture here is a consequence of this. And it's been mentioned before, Voevodsky was awarded the Fields Medal for doing this, and it created this whole new field of motivic homotopy theory. And one of the things happening in motivic homotopy theory today is people are trying to go back to these early papers of Milnor where the basic relationship between geometry and homotopy theory was established, and try to find analogs of all those relationships. And nobody yet knows an analog of the formula I started with in algebraic geometry, but it would be a very exciting thing to know about. There's another thing I'm dwelling over this slide because this thing I've labeled Milnor conjecture 2. I want you to appreciate how daring this was. I mean, it was daring to undertake to classify all exotic spheres. This is a conjecture. Notice this is a conjecture about all fields. This is not a conjecture about number fields. It's a conjecture about it's a conjecture about everything that can happen in one of the most basic objects in mathematics. It's unbelievably daring in its scope. Okay, so I promised you I would put all of these things together. So this is the formula that I've kind of draped this talk around. Theta equals pi times b. Theta stands for the number of these exotic spheres. Pi stands for an object from homotopy theory, a very different part of mathematics. And b is a constant of proportionality that makes a connection to number theory. It's just, to me, an amazing formula relating three completely different parts of mathematics. So there's one thing, though. This is in dimension 1 less than a multiple of 4. As far as multiples of 4 go, there's 3 other possible dimensions. And you might wonder what happens, what's the analogous formula in these other dimensions? So when Kervaire and Milnor wrote their paper, this is what was known. In dimension a multiple of 4, theta was related to pi by a much more simple constant of proportionality. This is actually really easy to understand, at least philosophically. If I'm in dimension a multiple of 4, that bounding manifold, the thing that I drew as a vase, has odd dimension. It has dimension 4m plus 1, so there isn't a middle. So the surgery will be unobstructed. You'll never meet a self-interacting dimension. And the 1/2 comes for a technical reason. In these other 2 dimensions, there you're encountering, the middle dimension is an odd number, and you're encountering that framing or that structure with these red arrows. And those factors, those mysterious factors of 1/2, these corresponded to, if you go through what I call the fundamental correspondence into homotopy theory, these corresponded to a very important and basic question in the homotopy groups of spheres. And this is the stand-in for the Kervaire invariant problem. So this is something that Mike Hill, myself, and Doug Ravenel solved a couple of years ago. And we showed that most of the time those factors of 1/2 are not present. So in the first 5 of those 6 exceptional dimensions, the factors of 1/2 are there. And unfortunately, we don't know what's going on in dimension 126. Okay, so Jack himself mentioned a paper that's appearing in the notices this summer, a differential topology 46 years later, where he summarizes this story much like what you heard in his lecture. I had the pleasure of receiving an email from Jack a couple of months ago with an early draft of the paper, and in this email he asked me the following question. He wanted to know, are all of these groups, is the smooth Poincare, do we know enough about the homotopy groups of spheres to know whether or not the smooth Poincare conjecture is true? In other words, are the homotopy groups of spheres non-zero? Always. And I have to confess, I felt like I'd been an engineer commissioned to send a rocket to Mars 20 years ago. And I'd spent that time with my colleagues exploring more and more elegant engines and more elegant dynamics and more elegant rocketry. And 20 years later, someone came along and said, well, does it go to Mars? And we were like, oh, I forgot about that question. And I had exactly the experience Hyman Bass described, that he came back and asked just a basic, simple question: are these groups non-zero? And I have to tell you, it's Mark Mahowald, Doug Ravel, and a group of us are working on this, and we're using everything we know, and we don't know the answer. But Jack asking this question created the homotopy groups of spheres is something full of anecdote and lore, and this question created a focus for it. It created a moment where it created mathematics. It created an occasion for us to take all of this lore and organize it and put it down around a problem that I kind of hope we won't be able to solve, because it'll be there for future generations who want to get interested in the homotopy groups of spheres. It creates an occasion for organizing all of this anecdotal information. So this was just a couple months ago, but again, a great question in mathematics creates mathematics. And so I personally want to thank Jack for asking me this and creating this amazing moment. So that's the end, although it's probably not, of course. Although that's one of my endings. I had an alternate ending I wanted to just leave you with, which is a picture of this formula and a little bit of a representation of the amazing interaction between three completely different areas of mathematics, and some of the places that the journey of coming to grips with this formula led Milnor, and then by fiat, all of the rest of us who studied his mathematics. Thank you.